Hi, good evening, everyone. Welcome. So this is the 42nd eBay Tech Talk already. Under eBay Tech, we sum up a few subsidiaries of eBay Germany. One of them is mobile.de. Igor and I are working for mobile.de. It's a platform for buying and selling cars. And Igor's topic tonight is design patterns for calculating user profiles in real time. Enjoy.
All right, thank you, Katya. So, welcome again. Thank you for coming. So, let's start. All right, so as Katya mentioned, the topic today is design patterns for calculating user profiles in real time. Quite a long title, but hopefully I will be able to explain it quite well during the next hour. All right, so just before I start, a little bit about myself. I joined Mobile at 2016, at the end of 2016. My main goal is to leverage and to build scalable microservices, to build the real-time infrastructure in Mobile, and this is my main focus, and also one of the main focuses of the talk today. All right, so as Katya mentioned, we are both working for Mobile, which is part of larger group called eBay. And Mobile is one of the largest online vehicle marketplace in Germany. We have approximately 43,000 dealers, which is almost all the dealers that exist in Germany today. And we have some dealers also outside Germany. We have approximately 13 million unique users visiting us each month, and around 1.6 million cars, so quite a large inventory. And approximately 1,000 changes to the ads, meaning like price update and any kind of update that the dealer can do on the car. We also have private sellers, not only dealers. So you can publish your car for free, or for example, if you want to sell it. So why actually presenting those numbers? Because it's important to understand that with so many people, so many users that coming each day to our platform, and with such big variety of vehicles, it will be hard for the user to find his next dream car. And our purpose in the data team at Mobile is exactly to develop some data products that we can help and leverage data and exactly try to help the users to find their next dream car. So the main focus today will be around one of the products that we are working, which is called user profile. So my agenda for today would be as following. I would give first some motivation about the user profile and why we actually need it, how it can help us to leverage and build better data products. What are the challenges of building such a scalable service that can calculate user profiles in real time and serve them in real time? What are the possible design patterns you can apply for designing such system? What are the architectures that we eventually decided to choose at Mobile? And afterwards, I would hope we have enough time and I would go a little bit to deep dive for some of the topics that's called the race conditions, which you will see is that it is something that comes because of the different select of design patterns that we do. So now it's quite abstract. Maybe some of you what you're speaking about, but a little bit patient and we will get there, and some final notes, of course. All right, so motivation. For motivation, everybody like numbers, so let's start with numbers. At Mobile, in our platform, each day we have almost around 50 million individual searches, and we have around 40 million view events, and I think in the last month I checked, it's even increased. So we have quite a lot of events, and all of that happening in one day. So approximately each day we have in general 100 million different events. And all of those events together are great, but separately they don't give us too much information. They don't give us too much intelligence, and we cannot do anything if we will look on single events or all of them together. So we needed to find somehow a way. How can we reduce this huge amount of events into something more meaningful, something that will give us insights? And that insights come in the form of user profiles. So each day we're taking all of those 100 million events, we process them with different processes and algorithms, and eventually we reduce it to 2 million daily user profiles. All right, so each day we generate approximately 2 million different user profiles. All right, so user profile. what it is actually, how it looks like. So this is a typical user profile that we have. The profile is actually expressing the user preferences towards specific car attributes, or you can call them also dimensions. For example, what is your favorite color? What is your favorite price of range, mileage? But it's not just numbers. We need to do, as I mentioned, something useful with it. So we can divide those two types of, we can divide those attributes to different two types. One, we can call it continuous variable, and another is discrete. And it's quite easy. The discrete variable is, for example, color, and we can say for user X, 30% of the cars he viewed blue and 70% are red. And for continuous variables is such price, we can say that we have a distribution, and we know that the ranges of the distribution is between 20,000 plus minus 1,500. Okay, so actually we try to express some sort of probabilities of a user to prefer a specific attributes of the car, and eventually we will combine all of those preferences together to try to come up with a recommendation for the user based on those preferences. Okay, but as I mentioned, we have here likelihood, and we're trying to understand what the user wants. So we have a lot of uncertainty as well. The question is how we represent this uncertainty. Okay, so for example, we can have a user that changes his mind quite fast. Today he looked for BMW, tomorrow for Mazda, and maybe after 3 days he decided, that Porsche looks interesting. What about users that don't have so much activities, that have only 2, 3 events, 4 events? Is it good enough? Is it many? Is it not many to drive any kind of estimation based on statistical models? What about new users that just arrived to the homepage or to any of the landing pages, and he still don't have any profile? What can we do for him? So this slide is a little bit heavy, and I have to admit this is not my slide. I stole it from my data scientist fellows, so it will look a little bit impressive. So I also have some equation somewhere, not just data engineering stuff. And the basic idea that we applying the Bayesian approach. So without going too much deep into the Bayesian approach and the Bayesian statistics, we can look on the Bayesian approach as following. We have something that we call the likelihood profile. The likelihood profile is actually the actions that you as a user coming and doing. You viewing some specific ad, you searching, you contacting the dealer. Based on those actions, we actually trying to build that profile that I presented. And it's sort of implicit profile, okay, based on your actions. Not something that you come and tell us, oh, I like blue, I like red. Okay, and then we can have on the other side the prior user, and the prior user is sort of our beliefs, how the world is distributed, what kind of colors people like, what kind of price ranges people like. So in other words, you can look on that sort of as average user. This is a user that we collect the events of everybody and until some degree average them. So we create an average user. Now, once we have the likelihood and the prior, right? So the average profile and your profile. What we can do, we can find with combination of both of them something that is called the posterior profile. And the posterior profile is actually a combination of those, and we give different weight to each side. So we give a different weight to the average user, and we give a different weight to your profile. And you can see here that the more events you have, the more impact it will be on your posterior profile, and the less you have, then the more impact of the average user you will have. And this is actually also the answer for users that don't have too many events. If you don't have too many events, then obviously at the beginning there will be more impact of the average user. If you have a lot, then with the time the impact of the average user will disappear, and most of the expression will come through your profile. And if you don't have profile at all right, we will just purely using the average user. All right, so a little bit mathematics, and no more mathematics, I promise. So motivation for real time, and I call it near real time because real time is just a definition of the business. Real time can be something that happen in 10 seconds, in 1 second, or in 20 seconds. It's just by definition of business. This is why many companies say today just in time or near real time. So why actually we need to calculate those user profiles in real time? Why do we need to serve them in real time? So we have different areas on which we can apply those near real-time functionalities. Because what we actually want to achieve is that once the user comes to the website, he doing searches, he viewing something, we want that will take almost immediate effect on what we will recommend him in the next step. We want to be able to affect on his action in the next page, right almost after that he done 2 or 3 views 2 seconds ago. So this is why we want to do it in real time. Okay, so in real time we can do much better personalization. When you do search, we can adjust the searches and use different scores and boost different properties of the car almost in real time, not to wait 1 night or 2 nights until we recalculate it. Okay, so the recommendations can be also much better, not based on something you have done last week. What it will help me, what you have done last week if you're doing it now today. But also think about it like that. In the edge case, for example, if you are a new user and you're coming and our service is unable, our platform is unable to calculate your profile in real time, but let's say we take the simple batch approach and we do the calculation only during the night. You are there now and you don't have the profile, so we will fall back to the average profile. So we cannot really apply stuff based on what you're doing. And maybe tomorrow you will decide that platform is not good for me, I will not be back. But wait, I already calculated your profile over the night, why are you not coming back? Okay, see, so you understand, calculation of the profile overnight is nice, but for many users that are coming only for 1 day, if I will not be able to catch them at that specific moment to try to convince them how good my platform, I will lose them. And that profile for the next day will be useless for me. All right. So what other challenges we have? So as I mentioned, we reduce almost each day 100 million different user events, user interactions into 2 million daily user profiles. And each profile have multiple dimensions. Remember the price, the mileage, the color, number of doors, airbags, all of those can be considered as different profile dimensions. In totally, we collected 20 profile dimensions that we thought useful, and we built for each user a profile based on those 20 dimensions. We keep the user profile on a daily basis for 60 days. What do I mean on a daily basis? You come today, you have any sort of interaction, we calculate the profile for you for today. You will come in 3 more days, we will calculate the profile for you for those when you will come in 3 more days. So we have a profile for T1, we have a profile for T4, and you will come in T7, we will have another profile for you for T7. And the question is, but why? Why do we need it? It just makes stuff more complicated and increase the amounts of data. The answer is quite simple. We wanted to have a flexibility. What you have done in T30 is not so much important as what you're doing in T1 and in T2. If we will keep the calculation of the profiles on the daily base, once the user come and the stakeholders that want to use our user profile service will say to us, okay guys, please give me the profile of that user based on the last 30 days, and I can apply different weighting functions between those days. And I can say those 30 is not so much important as 20, and 20 not so much important as 1. But what nice is that I can apply on the fly different weighting functions. True, I can recalculate profiles for user each day for time windows of last 30 days and applying those functions right away. But if tomorrow I decide that I want to do any kind of A/B testing, or if I decide, oh, that weighting was horrible, I will need to recalculate everything, and this is huge amounts of data. So by keeping each profile for a separate day, we can do those kind of combinations on the fly. This is first thing. Second thing, it's allowed to the different stakeholders to be flexible and say, for my service, I need user profile based on the last 7 days. For his profile, I need it on the 20 days. For somebody else, we need it for 30 days. So we're getting 2 flexibilities, the time window flexibility and applying decay functions inside the time windows that we selected. And this is why we keep each day for a period of 60 days, because this is the maximum that we at the moment give to our stakeholders. So they can ask a profile until maximum 60 days. Okay, so what we're getting eventually? 2 million user profiles generated each day. Each profile have 20 profile dimensions, and we keep each one for a period of 60 days. If you will multiply everything together, you will see that eventually in your database, you will end up with 2.4 billion records, which is approximately in our platform is around 350 gigabytes of data. And that is production data. This is data that need to be maintained and served in real time. This is not some sort of data that used for analytics, not some sort of unstructured data. This is important data for the business. Some other challenges that we have. We decided that we need to be able to update the profile within 30 seconds from the time the event happened, right? So this is, for example, a place where I mentioned near real time. So for us, up until 30 seconds, you doing view, 30 seconds passed since that event, we want that that event already will be part of your user profile. So after 31 seconds, once you come to the next interaction, that event will already affect on the results that you will get. But the responses from the stakeholders, they expect that the response of the user profile service, the profile that they ask for the last 30 days or 20 days with different decay functions, will be served in less than 50 milliseconds. And our expectation rate at the moment is 2,000 requests per second. Okay, some other challenges. So scaling out, as I mentioned, 2.4 billion, 350 gigabytes of data. For some companies, maybe it's not so big. Maybe for LinkedIn, it's one simple USB stick. For us, it's quite a lot. And the system needs to be scalable, first of all, from storage perspective. Today, we keep 60 days with 20 dimensions. What will happen if tomorrow we decide to keep 90 days with 30 dimensions? Okay, the system needs to be able to scale and to be able to keep with the pace of increasing data size, first thing. Second thing, all the calculations that we are doing, 2,000 requests per second, we need to be able to serve it in less than 50 milliseconds. All the stuff that I explained around the Bayesian approach, it's quite expensive calculations. Those posterior functions that we apply happening on the fly. So they are not pre-calculated. Each time that somebody requests a profile for a specific user, we're taking his profile, we're getting the average profile, and we're calculating the posterior. This is quite expensive mathematical operations that need to be done. So the system needs to be quite scalable. Availability. Even if we are not able to update the user profiles in real time anymore because something happened, something crashed, we want to at least be able to continue and serving what we have. So we don't want that the system will crash completely if only one of the sides is failing. So the most important side for us, of course, is to be able to serve it. So 99% availability, as everybody says, which is quite challenging, I have to be honest. And CPU intensive calculations, exactly as I mentioned, all the calculations, we need to take the data, we need to transform it, we need to calculate the posterior, the prior. This is quite expensive, and the system needs to be able to scale up quite well for that. Okay, so let's start to dig too deep inside the different design patterns. So what is actually a scalable system that can update user profiles in real time? Well, if you think about it in a nutshell, it's actually just a stream system with a state. It's just a stream processing system, stateful stream processing system. Our source of data is generated from the different mobile applications, web app, going to Kafka, and Kafka is our source of data. There we're getting all the events, okay? And then all that flowing through our stateful stream processing system, and inside the system we need to be able to update the user profile and to keep somewhere the state of our stream, which is the user profile. So in another words, for that system, the state would be our user profile, right? The state key can be combination, for example, from user ID, date, and dimension. Why? Because we want to allow to our stakeholders, as I mentioned, to get a profile for a specific user on a range of dates, but we can also provide them to say, okay, I want the profile and I need just the color, or I need the color and the price. So they can choose what they want. So this is why the combination of user ID, date, and dimensions give us exactly what we want. And the state update operation can be quite simple, such as counter increment or some sort of average variance update. Well, in practice, actually, variance update in stream is not so straightforward, and we were looking deep to see how can we implement it quite well. So eventually we found some nice algorithms that you would be surprised, exists already from the 70s, how to calculate running variance, and we took some Python library, we improved it, ported it to Scala as well, and for now it works quite good. Okay, so what kind of different design patterns can we apply for our state? How can we actually treat the state? How can we store the state? There are different options, and the most traditional option today is using some sort of external storage. Most of the time will be a distributed storage. Many typical choices for that is Cassandra and HBase, which are distributed, fault tolerant, and have many nice features. They can scale with the data size and scalability. On the other side, there is a more new increasing growing trend, sort of buzzwords, that many stream processing frameworks starting to use it, and that means that we will keep our state in a local storage, and the local storage can be in a form of, for example, simple hash map, some simple dictionary from Python that you know, from Scala, whatever. Okay, or embedded key value storage. RocksDB, for example, is really growing in popularity, and many frameworks are allowing to use RocksDB as the embedded key value storage. It's nice because it's in memory, but if you have more data than memory can take, it starts to spill data to the hard drive. Okay, so that is nice, but let's get familiar with each of those patterns separately. And let's start with the local storage option. So, as I mentioned, stream processing system, and most of the time it will be actually a distributed stream processing system because we have a lot of data that we need to deal, so most of the time we will use some sort of distributed framework, Spark, Flink, reactive Kafka, which is based on Akka streams, Kafka streams, you name it, what is more comfortable for you. Okay, and usually in a distributed stream processing system, the way how it looks like is that we have multiple workers. We have multiple executors, multiple workers. On each machine we can have multiple of those executors. For example, usually each executor is a Java JVM process, but for the simplicity, let's say that we have a server, a node, and each node is an executor in our distributed stream processing system. So each node is able to process a subset of the streams that we're getting. And usually most of the frameworks, knowing, especially when you're working with Kafka, and let's say Kafka topic have, I don't know, 10 partitions, usually those frameworks are able to do mapping one-to-one between the Kafka partition to the specific worker. So this is actually in Kafka the maximum level of parallelism that you can get based on the number of partitions that each topic have. Okay, so we have each node that is able to process a subset of the data, and eventually when you will do any kind of update to your state, that node will also keep a subset of your state based on a specific key, which means, by the way, that the events of specific user of a specific key always must end up in that specific node. Okay, so then we have that local storage and we update the state, so each node actually contains a subset of our state, which is based on the key value. Okay, so the next question is, okay, nice, now we know how to update our state, but how can we serve it? Because as I mentioned, we need to update the profiles, but we also need to be able to serve them. And now that we have many nodes, each of them subset of the state, how can we serve it? Answer is quite simple. On each of this node, we can expose a REST endpoint that will be able to access to the local key value storage. One important thing to mention, and again, is that each node have access to the local key value storage, and only the other node, for example, that one cannot access that local key value storage because it's local, it's embedded in the file system, so it's impossible. Which also means that the REST endpoints that you expose on each of the nodes can access only and only also to that local storage. So you're asking, okay, but when the user taking a request for a specific key, he don't know on which of the workers the key located, so how we should know to which REST endpoint redirect the request? So the simple is quite simple. Each of those is also will be used as a coordinator. So once you're requesting from that endpoint some specific key, that endpoint need to be aware of all the keys where they are located, and if it's not located on its local key value storage, it will redirect the request to the correct endpoint that will eventually return the data. All right. Moving next, external storage. Okay, so in the external storage, the story is a little bit different. We don't have anymore the local, we have one global storage, which means that we can also completely isolate it from the system, decouple it from the system. Okay, and what happens is that now all the distributed workers, when they need to update the state, they're going exactly to the same point, which means that 2 or 3 workers can access the global storage exactly at the same time, which can lead eventually to race conditions, what I mentioned in my agenda, which I will go a little bit deep further. Okay, so if you ask how exactly the race conditions can happen, is simply imagine a counter increment, two workers reading value 5, each adding, I don't know, one adding 2, another one want to add 3, and then they both writing that value back to the storage. Which one will win, we don't know, and we will see actually a nice slide that I prepared to explain that. Okay, but what is nice with the external storage is that we no longer depends on each of the workers from the perspective that, for example, the local storage is limited by size based on the worker. So if the worker is out of space, memory or hard disk, you're in problem. So if you decide to increase the state of the state, right, the size of the state based on more dimensions or more days, then you can be in a problem. Here on the other side, you can also increase always the external storage without affecting the stream processing system, the system that updates. So actually, until some degree, we're getting here full decoupling, which means that we can scale each part separately, and we can also get that requirement that we had, the availability. So for us, if the stream processing system fails, that system can still continue to live, and we can still continue to serve our profiles. And the way how we serve the profiles is quite simple. We just exposing REST endpoints. We can have multiple instances of the same exactly logic that sits on top of that external storage. Let's see if I missed something that I wanted to say. No. Okay. That slide I prepared today because this is another step in the evaluation that we want to try and to test. So it's nice that we have either the local storage option or either the external storage option, but what if we can have some sort of hybrid solution? Because as I mentioned, there are some issues which I will cover soon with each of them. I prepared a nice here a nice table to compare the different options, but eventually we can also try to think about a different approach. So we can say, okay, we're using the local storage for keeping not all the data, right? Because as I mentioned, we have 2.4 billion, and in the way how it was in the local storage option, without that you have the external one, it doesn't, I'm not sure if you'll be able to keep such huge amounts of data and continue to maintain it, and what happens if there is any kind of failover scenario and you need to recover and you need to reprocess. It can be quite problematic. So what we can do, instead of keeping always all the state of the user, we can have sessions of the users. So imagine the following flow. Some event of a user arriving to the system, and we check if we have already a state, if we have already profile for that user. And if we don't have the profile for that user, what we will do, we will load it from our external storage for the first time. And then we will keep that profile for a period of time, let's say 30 minutes for a session. So if during the next 30 minutes I will get more events of that user, I don't need to go again to my external storage to get the user profile in order to update it. I can get it already from my local storage, which is the access is quite fast. Okay, so each time I will update my profile during that session, I will always continue to flash it also to the global storage. Why it's actually important? Because in the option of the global storage and in the way how I described you the update of the profile. What is this update? Counters, right? So we have now profile, somebody had blue color 20 times, and now come a new event with another blue color, and we want to update it. The only way to do that update is to read what we have currently in the data store, that it is 20, add +1, and put it back to the data store, which is actually read before write pattern. So in addition to the race conditions problems that it can create, it's also creating high latencies and putting a lot of pressure on the database, because you're constantly doing read before write, and don't forget that on the other side you have the REST endpoints that also need to do a lot of read and serving the data. By applying the hybrid approach, we will reduce the number of reads that we're doing from the global storage. We will keep temporary for 30 minutes window time the profiles in the local one. Each time we have update, we will continue to flash them to the external storage, and then we will reducing quite a lot the amounts of read before write. Okay, so some comparison between the two different options. So let's start with latencies. So local storage obviously have quite low latencies. Why? Because we don't have any kind of network communication involved there. This is a database that sits on the file system, or in an even better case, inside the memory. The access is really fast, so if you want to get the state and to update it and write it back, it's quite fast. We don't have any kind of network bottlenecks, which is really awesome, right? Obviously, on the external storage, even if it's a distributed data storage, such as Cassandra or HBase, yes, they are fast, they are great, but still there are networks over there, and the more requests you sending, the distribution of network latencies and bottlenecks do what it's usually do, and you will get always 95% or 99% with really high response times. Resources and maintains. So I didn't give all the points for that to the local storage, simply because that distributed stream processing systems by themselves are not easy task to maintain. They are quite difficult by themselves to maintain. So in the local storage option, we're just getting rid of the external storage, which is nice, but we are still need to keep on maintaining our distributed stream processing system, which is not easy. And sometimes with those local storages, there could be also multiple problems. Obviously, if you will add on top of our distributed stream processing system a distributed storage, such as Cassandra or HBase, the complexity grows much more. We need to allocate much more resources. It's a separate cluster. You need another dedicated DevOps that maintain it. And we see in the last years that we're doing it, it's not easy. Cassandra, it's maybe nice for developers, but from DevOps perspective, it's not. Recovery from failures. Okay, so what happens if the stream processing fails? How long it will take you to do the recovering? Because usually what many of those frameworks that support the local storage option doing checkpoints, which means that they're writing everything to hard drive, and if you have a huge state, like 2.4 billion keys, once there is a failure and recovery, you need to be able to load it completely. And don't forget that in the local storage option, the entire system is bundled. So if you have any kind of failure in the update, and then you need to wait also time until everything is up, and that specific time, you're not able to serve the profiles anymore. So this can be quite important. If the business is quite sensitive for that kind of failures, it can be quite important. Also, what happened in specific frameworks that not able to treat good the exactly once semantics, right? So imagine that you have a checkpoint and something happened, something failed, you start to do the checkpoint, or let's say you updated your state, right? But the system failed before you were able to update Kafka offsets. Okay, now you are recovering again, and you're getting the state that you recover, like you updated the state, you had 10, it failed. Now you will read again the same messages from Kafka, and you can get duplications easily. So maybe the new Kafka version will make our life easier. They're promising exactly one semantics. Many people have a lot of skepticism, but as we say, time will show. And in the global storage option, so all the distributed data storages were built from the beginning on the fundamentals of high availability, of failover scenarios, of not having single points of failure. So usually they will be much better in that perspective, recovery from failures. State availability. This is exactly what I mentioned 2 minutes ago. If the option with the local storage failed completely, you're not able to serve your state at all. Or if you need to rescale your system, which we will speak a little bit below, if you need to rescale a system, in most of those distributed stream processing systems, you cannot just add more nodes and the life will be beautiful. Most of the time you will need to do some sort of stop, add more nodes, and restart your streaming again, which cause you a lot of lose, especially if your problem is not enough hard drive or not enough memory, right? Which can be prevented if you're using the external storage because you can scale it separately. Also, the problem of be able to serve in a higher rate. Okay, so the local storage, and you can expose the REST API, which usually those REST APIs coming naturally with those local storage solutions. But how scalable it is? Is it able to scale in updating the user profiles with high amounts of incoming data, but also in the same time to deal with a lot of requests for reading the state? Don't forget, it's the same system and the resources need to be split between these two functionalities. Okay, but on the other side, with external storage, we can scale each of those components separately. If we have much more read requests in the state, we can scale that part of the system and without touching the system that updates the profiles. And race conditions, I will touch it in a moment. So at Mobile, when we look on our requirements and what was important for us, we decided that the recovery from failures, state availability, and scaling out, this is what is most important for us. And based on those components, this is what we decided to go with the external storage option. So how it looks on our side. On our side, it looks like that. We have Kafka, as I already showed you all the way. For the distributed stream processing system, we selected Spark streaming. Flink is also a really good choice, but we had few issues with the data that I will show you later. Why, for example, we didn't went for Kafka streams, which is actually really good library as well. But to be honest, also some of the reasons that affected our selections are also political inside the organization. Let's be honest. It's not like you as a developer come and say, oh, I want that. Okay, you will get everything you want. Sometimes you have a team of DevOps that say, oh, we prefer that technology because we are more familiar. Sometimes there is another group in the organization that already started to use something and it's more easier for them. But we also went for Spark streaming because of the micro-batch approach. So as I mentioned, for us, it's good enough to be able to update profiles up until 30 seconds since they're happening, which the micro-batch approach exactly fits for us. But another advantage that we're getting with the micro-batch approach is that we're getting, let's say, during 15 or 20 seconds events from Kafka, and then we're reducing them to a single event. So if during those 20 seconds we have, for example, 20 view events of specific user, we don't need to do 20 times update to our state. We can first in Spark reduce it to one single update. And that can also release a lot of pressure from your data storage. Okay, so Cassandra we selected also because I had a previous experience with that. We know that it scales quite good. It have really good availability. It doesn't have single point of failure. It doesn't have the master-slaves architecture. It's quite battle tested. Many companies use it. There is a lot of community around it. Also a lot of community around Spark, which remind me the also issue with Flink. Back at the time, like 7 months ago, when I started to evaluate what kind of framework to choose, and we knew that we're going to work with Cassandra as well. The problem with Flink was, for example, that they didn't have the proper connector to Cassandra, and it was all only an alpha release. And I thought, okay, I can take a risk for the alpha release, fine, it will become better later. But still, when you know that in Spark you have the official support of data stacks, which is optimized driver, versus something that the guys from Flink writing, and there is not a lot of community around it, and if something happening tomorrow and you need new functionality, you need to open a ticket in Flink and wait and hope that somebody maybe will develop that one for you. So sometimes, maybe there is a better solution, and yeah, I think that Flink is really good streaming engine, maybe even much better than Spark. But the community factor is also important to take into consideration. If there is a good solution but not enough community around it, this can be a bottleneck, a serious one. All right. On top of Cassandra, we're using REST endpoints based on Akka. So Scala is the tool that we write all our microservices. Scala, from its name, scalable language. Akka have a really nice support. Akka HTTP is, in the last year, really starts to be really popular and having a lot of features inside, and it can scale quite well. It works really well. And everything is orchestrated by Mesos. So Mesos was not our choice. It's when I came to the company, Mesos already were used. So this is just a fact that I accepted, and we use Mesos, which is quite well. I don't see any kind of problems with that. All right. So as I promised you, a little bit more deep dive into race conditions. So a little bit flow to explain what is exactly happening in race conditions when we're using the external storage option. So imagine that we have two workers in our distributed stream processing system, and each of them getting event of the same user at the same time. So we have one that getting color red and another that getting color blue. And you ask, but how that can be? How you can get two view events of the user exactly at the same time? Impossible, right? Well, life is a magic. But no, seriously, network latency, data centers, Kafka producers, Kafka brokers, all of those can cause a lot of latencies, which eventually can cause even that something that happened first will arrive second, right? This is why maybe you see in many stream processing systems why Flink was supposed to be much better than Kafka, because it supports event time, not the time that the event arrived to the system, but when the event is actually happened. In our case, that sequence is not really much important, but for some cases it is. Okay, so this is explain how we can get theoretically in edge scenario for two workers, two events exactly of the same user. Also, think about it like that. When you usually come to the website and you have some list of searches and you see two interesting objects and you want to compare them, what usually you do? Do you click and go back and click again? No, you open it in a new tab, right? Which is happening quite fast and trigger events. We see events that happening in like milliseconds difference, which is exactly what can cause for those situations. All right, so enough quatsching, as we say on Deutsch. So the current state in our database, let's assume we have already a profile for that user, user X, and let's say we already have their color blue equal 2. So now we have two events that are arriving exactly the same to two different workers, and that is the flow that's happening. At T0, we're getting the profile for the user X, which means that the two workers will see color blue. Okay, so let's assume there is some sort of delay. So in T0, they execute a request exactly at the same time to Cassandra, which means that Cassandra will return them color blue for both of them, right? But maybe due to some network delays, one getting color blue after T1, one after T2. But nevertheless, both of them still see color blue 2. Now we have an update process. So in T3 is the first worker doing the update on the state of that user, and in T4 we have update of the second worker. Okay, and then let's imagine that exactly at the same time they trying to write the new state back to our external storage. Okay, so what it will be? Who will win? We don't care. The state will be incorrect anyway. It doesn't really much important who will win, because we lose. We don't get the accurate results. Okay, problem that implied because of selection of that kind of specific design pattern. The question is, do we have a solution? Like always in distributed streams or in distributed networks, approximately. Okay, so what kind of workarounds can we do in order to overcome that problem? So we can have two main approaches. One approach is to say we need to cause our stream processing system to each worker to be able to update in a sequence the event of the same user, which means that we need to make it somehow happening that all the events of a specific user will come always to the same worker, and that worker will process process those events in sequence or will aggregate them to one single event. Then we will prevent that situation that we have exactly at the same time two different workers trying to update the state for exactly the same user. So this is one main approach. The question is how to do it. We will see. The second approach is completely different mind of thinking. Don't think about stateless, stateful system. Think about stateless, a system without state. Think about how we can design actually a system without a state at all. For example, by persisting to our storage only the deltas of the profile. So for example, you have, for example, profile now in database is 2. Okay, so now some event happening, we will add that event, and if there is another event, we will add that event, and later the layer that serves the profiles, that's the layer that will do aggregations on the fly. We will see that as well. Obviously, each approach has its own advantages and disadvantages. Let's start with the first approach of making that each worker will process the events of the same user in sequence. So imagine the following situation. We have 3 Kafka partitions, okay, for single topic. And you can see that, well, I promised not to go there, but I will jump fast. We will see that we have 1, 2, and 3 partitions. And in each partition, we're getting events of users. Okay, so the green is, let's say, green user, blue user, red user. So it doesn't indicate on the color that the user selected, but it indicates on the user itself, like user ID. Okay, so the question is, how can we actually make this sequential processing by each node? So we can reshuffle the data. Actually, this is the most simple solution. You put another consumer on top of your original Kafka topic, and you reshuffle the data by user ID. And if you reshuffle the data by user ID, Kafka guarantees to you that all the events of the same user will always end up in the same partition, unless later you add more partitions, but this is another story. So, but basically, if you repartition by user ID, for example, then you end up with the same events of the same user in the same partition. And as I mentioned, the stream processing system knows to do the mapping between Kafka partition and the worker, and which means that each worker, it will be guaranteed that he will process all the events of the same user. We will never have a situation that event of the same user goes to different workers. Sounds nice and easy, right? But you need to know your data patterns. And what I mean by data patterns, we have a look on the data. And I started to ask questions when I came to the company. But why? Why you don't repartition from the beginning to Kafka by user ID? Why you don't send the data from the beginning by user ID? And then I done some analysis. And what I discovered is a lot of bots that have the same user ID. So just that you will get a little bit impression of what I mean. The analysis shows that 99% of the users having each day up until 100 events. But that 1% that remains can have 10 until 50,000 events. You know what will happen to your brokers and to your Kafka partitions if you partition by user ID and end up with one of the bots? Is the German kaputt? One of the broker will go out for vacation. So this is a problem. So many companies, especially Kafka Streams, for example, in order for Kafka Streams to make those stuff work, in Kafka Streams, each worker is actually independent. They're not able to share any kind of data between them, which means that you need to repartition by key from the beginning. But what you will get that one worker constantly works and the other are resting. And you will get that the Kafka broker maybe go out because he have too many data. Okay, so if you know that you have a scenario that you don't have too much bots, if you know that the data can be equally distributed among the Kafka partitions, if you know that you can filter bots from advanced maybe, then you can go for that approach. In our case, we have a service, we use Akamine for detecting bots, but we didn't want it to remove the data from the stream because it's important for us for other analysis of exactly analyzing those bots and how much good Akamine or any other individual algorithms. This is one thing, but even Akamine is not perfect. Even Akamine leaving us 20% of unexplained traffic with 20 until 40,000 events per day. Okay, the other option that we can do is repartition, not the data source, but during the stream process. So as I mentioned, if you will use like frameworks like Flink or like Spark, we can have the different repartition over there, right? So we can reshuffle the data actually inside between our workers. So we're getting, again, the same situation, but we don't repartition before the data goes inside the workers, but we repartition inside the workers. Okay, but you will ask, but what it's helping you? Still getting up in the same situation, because once we repartition inside our workers, we will still have one worker that getting most of the events. So you will see then in your distribution of times what time it took to the worker to complete his task. You will see that one is completed in 2 milliseconds, another completed in 3 milliseconds, and one completed in 1 minute. Okay, I'm exaggerating, right? But still, you are in the same situation. Okay, so but how can we still overcome it? We can add actually a reshuffle with reduce function, and this is what exactly we're doing. This is how we're leveraging Spark. So now, instead of just reshuffling, let's reshuffle with reduce. So eventually, this will end up with all the 5 events of the green user merged to 1 and the red merged to 2, okay? So then it's done really nice, because if you use the correct reshuffle function in Spark, for example, reduce by key, it will first do the reduction locally, and then will reshuffle and do the reduction one more time, which means that you don't get any more that kind of skewing data problem. And still, look, we will have eventually each worker having event or events of the same user, only he. So we will not have again the situation that 2 workers may have 2 events of the same user that they will try at the same time to update to our external storage. Okay, and the other approach, the last approach that I mentioned, the stateless stream processing. So in that situation, what I meant by adding deltas is means that we have a log structure, especially Cassandra, it supports log structure. This is why Cassandra is really good at writes, because it's just append data. Okay, so what we can do each time we're getting events, we will not try to read, we will not try to update anything, we will not put any kind of pressure on our database, so we need to do read before write. We will just append what we get. We're getting event from the green user, we will append it. We're getting event from the red user, we will append it. Obviously, you need to take both here into consideration, otherwise you will get inside Cassandra one partition, one key that it is really huge. But okay, we will do it, but eventually then the question is, but how eventually you calculate that user profile? You need still to reduce it, and the answer is that the REST service will do it. So the REST service will read the events, he will do the reduce step, will do the calculation, and will serve it. Apparently seems nice and good, and for some cases it's indeed good. The problem that first of all you will have some network bottleneck here to read those 100 events per day that you happened, and remember, we having the approach that we need to calculate user profile based on, let's say, last 10 days, which means that for each day in those 10 days we need to read all the raw events, all of those deltas, and to do the aggregations on the fly. It's nice, it will work, I promise you. I can have many of those REST endpoints to make it much more scalable, but I almost guarantee you that we will never be able to reach the 50 milliseconds response times. So this is the trade-off. So again, it also depends on the use case, but that can solve many other problems like release load from your data storage and from your DevOps, most important. All right, so some final notes. So as you saw, there are many different patterns that you can take to tackle that problem. And each solution will lead you to another set of problems, another set of challenges. Sometimes you will need to be really creative, think out of the box to see how you solve it. Sometimes, to be honest, you will not find a solution. So then you need to go back and review again everything that you've done. But in any way, it is really important to have a deep technical review of the existing solutions that are today in the market, all the open source, or if you're ready to pay money, and to understand really good the pros and cons of each of those technological solutions. Because once you know exactly which of them doing what and how, only then you can really tune for your use case. But it's not adding up there. It's not good enough to know just technical details about your solution. It's also important to see the business requirements. And only when you understand also your business requirements, when you understand your stakeholders, what they want, how they want it, because this is the most important factor. You build your systems for them. You don't build your system for yourself to say, oh, look what kind of system I just created. You build the systems that the company can use and leverage in order to achieve its business goals, right? So only when you be able to understand both of those requirements, the technical review and the business requirements, only then you can come to the perfect solution. And even not. And just a little bit like some sort of, I don't know, philosophical thoughts, I don't know even, but even if you already came up with some solution and you think it works good and you think you built the perfect system, never do it. Always doubt yourself, always look for new possibilities on the market, always look for new technologies, new development, and always try to think, would that help me? Maybe that can help me to improve it. Maybe it will make my life a little bit easier. So you never can sleep on your watch, right? You cannot always say, okay, I have built something, it's great, it works, it's excellent, that's all. And up until now, even that systems that I described for you, I'm still doubting and I'm looking constantly for maybe something that I can do better. I'm constantly looking for any kind of bugs in the logic or in the implementation. And as a proof, you saw the slides that I added today for the hybrid approach. We're thinking about it, we're evaluating it. We don't know still if we can do it or not, because we use Spark on Mazor in private cloud, which is not on top of HDFS, but on top of OpenStack, which is using its own file system. So we need to evaluate it. We need to see if it's good. We need to see if the community supports there, if it will work properly. Yeah, and the last words, as Katya mentioned, we are hiring. We're looking for data engineers. We're looking for data scientists, backend developers, Java, Scala. Okay, it's we're growing. The data team is growing. We recently went through some reorganizations. So we're constantly growing and looking for talented people. And if you would like to hear more, you are all welcome, and yeah, if you have questions, please, I would be happy to hear. Thank you.
Could you describe a little bit, like the whole thing is like a huge undertaking, so what did you gain from a business point of view, from a user experience point of view?
There are multiple places. So this system, first of all, important to say that it is still in, I don't know if to call it prototype or not, but we are still running A/B testing to make sure that it is stable enough. But yeah, we saw quite a high, will depend on the business what is high, but we saw high in our definitions, which is I cannot expose, of increase rate in conversion rate. So we started to put recommendations of cars in places, for example, when you save a car to your favorite list and you come back after 2 weeks and you want to open it, but it's already sold, so it's not there, you will get page 404. So instead of just showing 404, we also show recommendations, okay? And we saw a large increasement over there. We also going to use the user profile for example, for sorting results for you. So for example, we can leverage it for autocomplete of search. So you come and we have many dimensions: color, price, mileage. Maybe you don't know from the beginning, or you don't want to fill all of those filter boxes from the beginning. So what we can do, we can take your profile and we can do it implicitly for you. So you can just put the price, for example, and number of doors, and we will see based on your profile, but also we will limit the price ranges like that and like that, based on the profile. And we see that we see really increasement in the conversion rates based on what it was before. And we're trying different approaches, so it is really affecting. Otherwise, we would never be busy with that project for 8-9 months.
I saw your notes on the race conditions, so you evaluate it like 2 ways: either you just store the data or you fill them, yeah? Just one way out of my head, which is used in dynamically, for example, conditional updates and some kind of optimistic concurrency. Did you evaluate it?
Yeah, it exists in Cassandra. So Cassandra is not transactional database, but those kind of conditions lightweight transactions. This is what they have with if conditions, but they are still complex, and they also putting a lot of pressure on the database itself. And when I had a discussion with DataStax guys and I explained them the problem, we had a lot of hours of discussion, and actually even inside the DataStax community they are divided, and one said, yeah, you should better take care of those race conditions from the application side, whether somebody else said exactly like that. No, you should use our lightweight transactions to tackle that. So I know that those transactions make life actually a little bit harder and make the work of the database even harder. So I saw that I can prevent it from the application level, and this is what we selected. To guarantee that I would prevent it for 99.9%, I'm not sure, but even if it will be only for 99%, I think we can still live with it since it's not transactional databases. But to come to situations that you don't think about it at all, this will be even worse. All right, then. Enjoy the rest of the evening. And I am here if you have any questions about job, about the presentation. Please come, ask. I will be happy to share. Thank you.